Hello, today we're going to talk about organic wastewater resource recovery plants. These plants are self-sustainable and climate positive. My name is Francisco Valdes, and I'm the creator of this technology along with a talented group of engineers. And this technology was developed for AmphiBIO Technologies. AmphiBIO Technologies is a socially committed company which is looking to improve people's lives through the creation of innovative solutions for resource recovery from wastewater. Our goal is to achieve the triple bottom line of sustainability. That means that our projects have to be good for the people, good for the environment, and good for the economy. We try to comply or contribute to as many goals of the United Nations Sustainable Development Goals in each of the projects that we do. As a matter of fact, in a complete project where there is efficient use for water in agriculture, water reclamation from wastewater for irrigation, and water reused in irrigation, we can contribute to as many as 14 of the 17 SDGs of the UN. Our philosophy is to work with and for nature. That means that we take advantage of the biological processes that there are, gravity and the solar power that we have for free every day. Carbon footprint and sustainability are the main goals. We go with biological processes mainly, especially with anaerobic processes, which generate biogas, which is a form of energy. And then we use anoxic aerobic processes when needed, but those have a cost from the energy point of view. So we try to do as much as we can with anaerobic and as little as needed with aerobic anoxic. Physical processes are also used when they're convenient, and we try to stay away from chemical processes as much as we can because of their cost and their carbon footprint. With those objectives in mind, we developed the multimedia bioreactors. This technology, we believe, is the most efficient way to biologically treat wastewater while also recovering very high quality effluent, green energy in the form of biogas, and a nutrient-rich substrate that can be used as fertilizer. We have over 10 patents already introduced with this technology, and we're working on 2 more of specific applications. And as I mentioned, this technology was created by myself with the collaboration of a group of engineers. For biological carbon reduction, there are the aerobic processes. We take 100 kilograms of COD, and if we add some energy in the form of aerators, we can break down the carbon to CO2, and some of the carbon will settle in the sludge. A percentage of the carbon will remain in the effluent of the process. Normally, we can remove from 90 to 98% of that. So the process is a proven process, easy to replicate, and produces a fairly good quality effluent. Is not very good with high loads, industrial effluents, for example, and is somewhat sensitive to toxic inhibitors. But the main drawback of this process is that it consumes a lot of energy. So that becomes prohibitive for some economies to operate. And also the sludge that it produces is rich in carbon and has to be dealt with. And that also in turn consumes energy. So it's a proven process, but expensive in general. There is another way to reduce carbon in an effluent, and that is with anaerobic processes. Anaerobic processes require a little input of energy in the form of mixers and pumps, and the breakdown of carbon goes mainly to biogas. So we will have about 80% of the carbon converted to methane and CO2 and other trace elements. And the sludge that we'll extract from this process is normally going to be with very small carbon content, fully digested, and normally with just disinfection we can use it for other applications. The effluent, however, is not going to be as polished as an aerobic process, but still we can look from removal rates that go from 80s to 90s and even 95s in high strength, high load industrial influence. The advantages of this process is that it can digest very high loads, industrial waters, for example. It consumes a very small amount of energy. It produces only a tiny amount of sludge and is normally fully digested. And the most interesting part is that it produces a biogas, which is a form of energy. We can produce from a kilogram of COD, roughly 0.25 meters of methane, and that is being conservative. So in this example, with the 80 kilograms, we produce 20 cubic meters of methane, and that can be converted into 40 kilowatt hours of electricity and 40 kilowatt hours of heat. One of the disadvantages of this process is that it does not produce a polished effluent, and the design is not as easy or straightforward as with aerobic processes. And I would say the main drawback of this process is that in the past, people designed anaerobic processes that were venting to the atmosphere. And that is bad in many ways because first you release methane into the atmosphere, which is a potent greenhouse gas. And also the hydrogen sulfide, which is another causing gas, the rotten smeg of anything organic decomposing is mostly the hydrogen sulfide, is also harmful for the health. It's not only the other that should bother us. In high enough concentrations can affect your health, and if it's really a high content, I would say anything above 100 parts per million, it can be even lethal. The AmphiBIO resource recovery process takes an anaerobic process up front, sometimes with multiple reactors in series, so we really try to squeeze all the carbon that we can from the influent and convert it into biogas. We will produce a sludge which is digested, and the effluent we will need further treatment. That effluent goes through aerobic processes that are carefully designed to be as efficient as they can, and we will have an input or a requirement of energy, but on a lower base. Instead of having the 100% of the load with that, we might be having a 15% or 10% of the load to be dealt with aerobically. And then the carbon breakdown will be similar to any aerobic process. We're going to produce some CO2, some undigested sludge, and then we're going to have a pretty high polish effluent with all the steps that go in between the anaerobic and the aerobic. The biogas that we produce in the anaerobic stages would be enough to supply, most of the times, the aerobic process and the pumps, mixers, UV disinfection systems, and so on. And the heat can be used to keep the anaerobic process warmer, which in turn will have it more active and performing better. The sludge that we produce in the aerobic, which I mentioned that has to be dealt with, in our process, we basically recirculate it to the equalization tank. That way it goes through the system, and eventually it will land in the anaerobic process, and when it's fully digested, will be extracted here. The process is so efficient that with the energy produced in the anaerobic stages and the energy requirements of the energy consuming stages, we can have a surplus most of the time. And that way we achieve the financial sustainability that we also require. Our name comes from that, from having strong processes in both environments, anaerobic and aerobic. Okay, now let's talk about biological nitrogen reduction. There are two ways to deal with nitrogen. The most common way, and I would say the only way up to 1995, other than chemical, would be with the conventional nitrification, denitrification. In that process, we take the ammonia that comes in the wastewater, and we add oxygen to convert it first to nitrates and eventually to nitrates. Nitrates is 1 nitrogen and 3 oxygens. This process is called nitrification, and it does require oxygen. If we set this as the base, as the reference point, we will need about 4.57 grams of oxygen per gram of nitrogen in the form of ammonia. And then to remove these nitrates, which we cannot leave in the water, we need a different set of bacteria that performs under anoxic conditions. And for that process, we need carbon, because this bacteria is heterotrophic. That means that it requires carbon for its operation. And normally we have to leave about 4 grams of COD per gram of nitrogen that we have to remove. The way to deal with nitrogen biologically is called partial nitridation deammonification. It's also known as anaerobic ammonium oxidation. Here we take a portion of the ammonium and convert it into nitrates in a process that is called partial nitridation. Since we're not converting the full amount of ammonium in the wastewater to nitrates and then nitrates, the requirements of oxygen are way smaller, and it comes out to be about 1.7 grams of oxygen per grams of ammonia. That is 37% of the oxygen required in a full nitritation or nitrification environment. The nitrates and the ammonia combined in a process called deammonification, where other bacteria will combine the nitrogens into N2 as a gas and those are released to the atmosphere, and the hydrogen and oxygen is combined into water. There is no need to go with the full path of nitrates to nitrates and then the anoxic stages of denitrification that were used in the past, and therefore the process is more efficient. If we take the two processes and we compare them side by side, it becomes evident that the reduction in oxygen required is quite significant, 62% less for the partial nitridation deammonification. Also, we require less carbon, which is also good news in our particular process design, because we can go harder in the anaerobic stages without worrying that we deplete the carbon for an anoxic stage in the conventional scenario. Our chosen way to deal with phosphorus is to enhance it biological phosphorus removal. In this process, we take the phosphorus that is coming into the influent. Part of it is going to be settable, and that will go to the bottom of the separator or the anaerobic reactor and be extracted later on with the sludge. But part of it is going to be soluble. And what we aim to do is to separate that phosphorus from the effluent. The way we do that is in the anaerobic stages with a combination of compounds that form there, such as volatile fatty acids and alkanodes that also form there. We create what is known as PAOs, which is phosphorus accumulating organisms. Those PAOs, when they go into an aerobic stage with the oxygen, absorb some of the soluble phosphorus and attach that phosphorus to these PAOs, and they become settable components. In the clarifier, only a small remaining amount of phosphorus is going to be soluble, and the bulk of it will settle with the PAUs in the bottom of the clarifier. That is later moved to the equalization tank, and then it ends up again in the solid separator and the anaerobic reactor, and is extracted with the sludge to be used as fertilizer. Okay, so let's take a look at the traditional way of looking at wastewater. Wastewater normally had to be treated. In my mind, that sounds like dealt with, and it was seen as a nuisance more than as a resource, even though it's 99.9% pure water in a typical municipal wastewater system. So normally we take the wastewater, we treated it to a level where it would be non-polluting, and then we dispose of it in a river, lake, sea, or even inject it for surface absorption. The way we look at it is wastewater is mostly clean water. So we have a system that breaks down all the components in the wastewater, and we end up with non-polluting water, we end up with biogas, and we end up with the sludge. And that with recovery subsystems, we can bring to a level where we can be, the water, for example, where it can be used for several applications, unrestricted or restricted irrigation, industrial applications, and even indirect potable reuse. The biogas, on the other hand, is going to have some things that we have to deal with. One of them is foam, and the other one is hydrogen sulfide. But those are fairly easy to remove. And once we do that, we can use the biogas for heat or a combined heat and power system. If we want to use it as a compressed renewable natural gas, we have to also remove the percentage of CO2 or bring it down to a very small level, and humidity in order for it to be compressed and used properly. And on the sludge, it's pretty straightforward. We have to thicken it, we have to dry it, and then we have to disinfect it, most of the times through pasteurization. Once we have disinfected sludge, rich in nutrients, it can be used for gardening and agricultural fertilization. In short, in the AmphiBIO resource recovery process, we take wastewater or organic waste and we convert it into clean water, green energy, and not nutrient-rich substrate. All these components can be sold, should be sold, and reused. That way, we can have income to operate the rest of the process and make it financially self-sustainable. All the process is designed with efficiency as one of the most important parameters, trying to have the lowest cost of operation in the system. Also, with a policy of little to zero residues. Everything that comes into the water can be converted into something useful. And in this type of systems, when we're climate positive and we're trapping carbon, the carbon that comes in the form of waste in the wastewater, we can have carbon credits. And this is becoming an increasing source of income for green companies and green enterprises. Okay, so if we look at the multimedia bioreactor, what makes our reactors so good? Number one is that we pack a lot of biomass in our reactors. We have the reason why we're called multimedia is because we pack granular biomass, we pack diffuse biomass, and fixed film in the same reactor. So we have a whole bunch of bacteria doing the work both in the aerobic and the anaerobic stages of the process. The retention times, since we have so much biomass in one of our reactors, normally are shorter for both water and also the solids that we're digesting, the sludge that we separate. So we're very efficient as far as SRTs and HRTs. We have a special construction in these reactors where we use a double wall GRP reactor, a glass reinforced polyester with a polyurethane, high density polyurethane foam core, which is very good for insulation purposes. So we can have these reactors in cold environments and the water inside them would be still at a good temperature to perform well, even under anaerobic conditions. We have very good contact factors and mass transfer efficiencies, and the use of an expansion system and also a column recirculation system. And there is no way that our water can have a short circuit in the reactor. Short circuits mean that when you have water coming in the reactor, by some accident can go out of the reactor quickly without having enough exposure for the organic content to be digested. And here we inject the water sometimes down the column of the reactor, and it has to go all the way down to the bottom of it and then come back up to go out of the reactor. So there is no way that we can have short circuits. Therefore, our removals are very interesting. And normally we automate the process to reduce human error and to have the performance maximized. The more activity that we have biologically, the more we're going to be removing organic compounds and producing energy in the anaerobic stages, and the better effluent that we're going to have. For example, in an anaerobic stage, if we remove 90%, we leave only 10% of the work for the aerobic stage, and that is going to require less energy in turn to become a reusable effluent. The configurations that we manufacture these MMBRs in is first the prefabricated plants, which go from 0.6 meters, 2 feet in diameter, and 6 meters in height. And then the largest that we can make in the prefab series for transportation limitations is 3 meters in diameter and 18 meters in height. That means 10 feet in diameter and 60 feet in height. After that, when we have large projects, we can go with on-site fabrication of reactors. And there we don't have a set limit, but I would say the range goes from 4 meters in diameter to 28 meters. And then the heights typically are in the range of 12 to 24 meters in height. Sample applications of these systems, for example, in a municipal system, 60 liters per second, which roughly translates to 1.5 million gallons per day, with 1,000 milligrams per liter of COD in a nutrient preservation arrangement, will consume about 980 kilowatt hours per day. The arrangement that we have, all the reactors that we see here with covers and with the foam traps and the pressure relief valves and everything, all these are anaerobic, so that means that they produce biogas, which is energy. We have a deep column separator, which to separate water and solids, and then we have aerobic stages. Here we have 3 trains of 20 liters per second each, and then at the end, each train has an aerobic stage, and then lamella clarifiers, disinfection, and so on. But the resources we recover is going to be roughly about 2,200 kilowatt hours of energy that we can produce with this system. We will recover about 5,000 cubic meters per day, and a small amount, but still, useful, of 300 kilograms of nutrient-rich substrate per day. The breakdowns of energy, all the yellow stages are done in the anaerobic stages, and these produce energy. And then the blue are the aerobic, and the darker blue is the clarifier. So these are the removal rates in the different stages. The yellow is energy producing, the blue are energy consuming. And disinfection as well consumes energy. But the balance is we have an energy producing wastewater treatment plant. In industrial plants, for example, in the tequila vinases industry, where we have high loads, the potential for generation is by far higher. Here, where we have a smaller amount as far as flow, but with a really high quantity of carbon, 55,000 milligrams per liter of COD, in a nutrient preservation environment, we consume about 380 kilowatt hours, but we produce up to 3,000 kilowatt hours of electricity with this arrangement. The water produced for irrigation is smaller because it's a low flow, but the substrate that we recover is more important per cubic meter than with municipal waters as well. So these are really interesting projects. If we look at the removal rates in this particular application, we can see that it's almost all yellow. That means that the anaerobic stages are doing by far most of the work. We get above 90% reduction of BOD, COD. Solid, suspended, and fat, soils, and grease are either separated or digested mainly in the anaerobic stages and the column separator. And nitrogen and phosphorus, up to 60% of it is taken care of with the anaerobic stages as well. One interesting thing here is that the amount of energy that we produce in the anaerobic stages is in the neighborhood of 3,000 kilowatt hours, and we consume only 380 kilowatt hours per day. So it's a energy producing arrangement, and that helps greatly with the sustainability of the process. Here's what one of our reactors looks like in real life. The one that we're showing here is a 3018 reactor, which is 3 meters in diameter and 18 meters in length, since it's on the side. And this reactor is manufactured with 2 walls of fiberglass reinforced polyester. It also has a thick core of polyurethane, high-density polyurethane foam, which gives the reactor structural rigidity that it's outstanding, and thermal properties are very good for this type of application. On top of that, the resistance to corrosion of the fiberglass reinforced polyester are also great and much better than any type of steel when there is hydrogen sulfide present. So the life of our reactors is significantly longer than any other construction, whether it's concrete or steel. Our reactors, once they're manufactured, they are transported to the place of installation. In this case, we can see that our largest reactor of the prefab series can be transported in a drop deck stretch bed trailer. And even though it has excess of dimensions, the freight, since is not very heavy, is quite simple. Once the truck reaches the installation point, the same crane that is used to unload the truck is used to place the reactor on the concrete slab where it's going to be attached. Once the reactor is set in place, it's then clamped down to the concrete slab with the steel clamps to hold it securely in place. Once all the reactors are clamped on the concrete slab, we proceed to fill the excavation to recover the ground level that we had before the installation. The more we can put the reactors underground will lower our pumping requirements and therefore the cost of operation. So finally, let's compare an MMBR versus a conventional wastewater treatment plant, in this case, an activated sludge plant. First, we're going to see that the energy requirements are in the neighborhood of 80 to 90% less of a traditional plant. Personnel, we're going to require probably a third less, about 30% versus a traditional plant. Basically because everything here is contained and closed and there is less work to be done. It's more automated than a typical plant. Chemical supplies, we deliberately try to avoid chemicals. So in the best case scenario, it's going to be 100% less. Due to the vertical nature of our reactors, the occupied space is also much, much smaller than any traditional plant, also in the neighborhood of 80 to 90% less. The initial investment we're going to be in the neighborhood of plus minus 20% versus a conventional plant. Sometimes we're the most economic option from the start, and sometimes we're 5 to 10 to 20% above a traditional plant, but where we have no competition really is in the cost of operation and in the resources that we recover. Starting from the water that can be sold and reused, the energy that we produce in the form of biogas that most of the times is enough for the whole plant and sometimes even a surplus. And a modest income comes from the nutrient-rich substrate that we can sell for agricultural uses. Well, I hope you liked the video. Thank you for your attention. If you are interested in this technology, contact us at sales@amphibiotech.com. If you're an end user, we will redirect you to a partner. If you are an integrator and are interested in the technology to use it yourself, please contact us. If you're an engineering firm and you want more information to specify this technology, let us know. We will help you. We will have other resources available as time goes by, also in amphibiotech.com. Well, thank you very much, and we hope to hear from you soon.